All right, thanks very much. I wish my handwriting was as good as Chris's, but well, here we are. So I'm Ben from Eclipse, and I'm here to talk to you about performance. So first of all, what is Eclipse? In a nutshell, it's an SVM rollup on Ethereum, and let me just unpack that for the next couple of minutes. So SVM, Solana virtual machine, C-level virtual machine, depending on your preferences, and I think you'll find both of these interpretations out there. What do we like about it? Well, I think there are a few things to like, right? So, and those are the kinds of things not necessarily found on the EVM side of the house of the divide or EVM2, nothing like that. So we find it to be quite a usable software stack. We find that there are more and more Rust developers in the blockchain ecosystem as a whole, and that's an advantage. And longer term, of course, we'll see people, Rust developers, that is to say, crossing over into blockchains who are currently outside of that space. So that's sort of one thing. Another one is that it's quite performant out of the box, right? So that's another sort of good thing about it we quite like. And we're settling on Ethereum, so we, as they say, inherit the security of Ethereum, but as with any kind of inheritance, you sort of inherit bits and pieces, right? And the devil is in the details. And it's not just the Ethereum part that we need to worry about, it's also, since we are using an alt DA, we're using Celestia for our purposes, performance-related purposes for the most part. We also need to be fairly careful about the actual security guarantees. Let me touch on that in just a few slides as well, but like in a nutshell, right? So this is what we are there to offer. Now, it's an interesting time to be sort of straddling this space between Solana and Ethereum as well. Why? So, well, a few things to point out. On the Ethereum side of the house, right, I'm sure you've been watching, various activities at the Ethereum Foundation and the role of rollups and the rollup centered roadmap and what's been happening there in the last several months alone. So what will happen, right? And where will specifically execution happen? This is one of the questions that's sort of key to our to the presentation here and key to our design. And of course, we are very keen to own the execution surface for the foreseeable future. So if Ethereum remains, mostly a place where liquidity rests and a way to deliver DA at a more attractive price point, amazing. We'd be very happy with that. But I think we are here to basically own the execution model and take it forward as well. Lots of interesting activity around ZK, and for a while I was working in the ZK space as well. So personally, I'm actually quite excited to see that going forward. I think a lot of the things we're seeing around ETH proofs, again, super exciting. I mean, if we actually get to real-time proving, I'd be very happy to see that. Of course, the question is at what price point, right? We can probably parallelize that enough to get us closer to real-time proving. The question is it going to be affordable? And as such, is that going to offer attractive fee structures to the end user as well? So we are optimistic, although there's an element of a hybrid rollup because of the way we do fraud proofs, and I'll double click on that in just a few slides. If we turn our sort of attention to Solana, and there's a Solana conference happening in just a couple of days next week, Monday and Tuesday, of course, Solana itself is chasing the performance chasing very aggressive, I should say, performance targets, right? So there are interesting presentations about sort of this notion of a decentralized NASDAQ from Anza, from the Solana Foundation, things of that sort. So lots of stuff there that's interesting that we are keenly watching. And simply put, the bar for performance will keep raising. Okay, so performance. So why, right? I mean, we've been hearing this phrase, Visa scale, and sort of goes back to at least 5 years, maybe more in this space, in the crypto space. And so, what do we care about and why does it matter? And my sort of simple answer to that is that more performance capacity opens up the possibility for new types of applications. Because in a sense, transfers, we have that problem, I would say, largely handled. when it comes to the types of applications we see in DeFi that I would still qualify as smart contracts by and large. That is to say, they are sort of, I mean, not always, but to a large extent, you can sort of fit them on a large screen and look at them and that sort of thing, right? So that's sort of the space we think about as a smart contract. And, that's all good and well, but the problem is that we've sort of stagnated. We haven't gone beyond that in terms of the sheer size as well as complexity of the applications that are getting built, and I think that's a shame. Because, as I'll explain in just a few minutes, in principle, the capacity is there, just not being utilized, and it's not being offered to the end developer but in a particularly sort of friendly manner, let's say. So who are some of the players? So lots of players, of course, on the EVM side of the divide, so to speak, right? So projects like Monad, Say, Mega ETH, there are some others coming up as well. I think that's certainly exciting to watch. And again, as I mentioned, just a few minutes ago, I mean, like much more performant ZK proving is ultimately becoming reality as well, despite what I said before, which is we still are largely optimistic with elements of ZK for supporting fraud proofs. So let me kind of cover some of our design choices. I already mentioned that SVM gives us a great starting point. It's already a pretty high performance runtime, and we're here to make it faster. Optimistic is ultimately a cheaper approach to take, and we're there to ultimately give a more attractive price point when it comes to fees to the end user. FastDA at the moment, 4844, is not quite there in terms of its throughput as well as price. So we've chosen to build on top of Celestia, and that's been going quite well. I'll show some pictures related to that in just a few minutes. And last but not least, we are not really focusing on geo-distributed consensus. I'm not here to talk about sequencing much. I'm not here to advocate for a specific approach. This is something that we probably will dedicate, another talk at another event to at a later point. That's not the focus for today. Okay, so this slide is actually quite important, at least to me. So what is it trying to tell? So currently, sort of almost independently of whether you take the EVM path or the SVM path, we are ultimately offering the developer a very, very thin pipe. This is not really drawn to scale, right? So on the left, we basically have the amount of compute that's being offered to a blockchain developer today. On the right, I'm showing what's actually available out there. And I think the best way to think about what's available and the domain that's been essentially capitalizing on that in every possible way is AI, right? Training, fast inference, all of these things. You see these things at the bottom of the slides. But let's take this, from top to bottom so you have a kind of better perspective here as well. So off-the-shelf hardware, what's available there? Dozens of cores are common on run-of-the-mill laptops. Hundreds of cores are fairly common as well on server sort of scale hardware, right? You can get it from the AWS, you can get it from other cloud providers, you can buy these things, yada, yada, yada. It's all imminently available. Hundreds of GPU cores, high-end GPUs, NVIDIA, all of that, AMD, again, there's a ton of parallel computational capacity that's out there, and it is, again, fairly affordable as well. Gigabytes to ultimately terabytes of RAM, not out of the question either, right? And sort of, again, has gotten a lot more affordable in the last several years. And then last but not least, some specialized devices, but let me mention that in just a minute or two. So then there's the cloud setup, right? So cloud hardware, so rack scale compute, that sort of thing. You effectively get even more cores. You have fast connectivity between those things. You have disaggregated storage. You can have disaggregated memory. All of these things are fairly exciting. And again, we have, ultimately like 15 years worth of research on how to program those systems as well. It's not just things like MapReduce, it's a lot of other things that happen at rack scale, if you will. And then the last one here at the bottom is what I sort of alluded to. So AI acceleration technologies. It's FPGAs, right? So Austin mentioned, accelerating SIG-verify with the help of FPGAs, but clearly that's one of many applications. It's also GPUs. ASICs, I suppose, depending on your workload, occasionally could be useful and helpful as well. But it's not only that, right? So there are devices like SmartNICs that actually offer computational power that's close to the wire, close to the network card, or on the network card itself. There are various designs that combine the network card with like some FPGA processing, or you can blast, data from effectively the wire to GPUs, right? GPU cores using RDMA and things of that sort. And again, all of these things are actually by now relatively commonplace when it comes to AI, right? I mean, this is the domain where a lot of these research technologies, if you will, have been deployed. And this is one of the reasons we have training that proceeds as fast as it does. And of course, we have like blazingly fast inference, right? This is where you see sort of this latency really getting squeezed. And things like, near data, right, near the hard drive, near the disk, and in-memory processing, of course, there for AI purposes as well. So again, just to highlight what I said just a few minutes ago, the point is that there's a tiny, tiny pipe on the left, and there's a gigantic amount of capacity on the right, and the question is, how do we bridge this kind of divide? Because if we could go, like, I don't know, even one, not to mention 2 orders of magnitude towards the right, I mean, things would be really quite different, right? We'd go beyond the domain of smart contracts to a space where you actually are programming larger scale, more interesting applications, right? And we're not there yet. So performance progress, right? This is where we are at Eclipse. So some numbers. I'm not going to show too many numbers in this talk, and we're just starting to release some of the measurements. So I'll give you a point to do that in just a few minutes as well. But this is the observed peak TPS, about 8,000 or so. So measurements show that, like, we can hit 100K TPS in the lab. And our goal is to get to the peak, right, over there on the right. This is what we call GigaCompute. And it's about 1 order of magnitude from where we are at the moment, so we feel it's actually all quite doable. Now, TPS, I'm not going to spend too much time on that, but probably not the best metric. And part of it is because it sort of focuses heavily on things like transfers, which is all good and well. But again, as I said a number of times already, we really want to give more computational capacity, more computational power to write bigger, more complex applications that run on chain. And so as such, we actually probably need a different way to measure these things as well. A few things to mention in terms of our foundation that I haven't done up until now. So yeah, SVM, Rust-friendly and existing layer of tooling, so that's all good and well. Parallelism supported. It is indeed supported. Question is, how well is it utilized, right? And it goes back to what I showed to you in the previous slide. We have tons and tons of cores. Can we actually even hope to load even a small fraction of those, right? I mean, you look at these utilization pictures, you see that like there are 4 cores being utilized for an average Solana validators. What happens to the rest of them, let's say, right? When it comes to Solana, though, I mean, there are some interesting applications like the blue chips I have mentioned here. So Orca, Jupyter, Camina are all great programs. And so what we get out of the box is the ability to migrate those over with very minimal effort, right? So we have a lot of these applications that can come over and run in Eclipse. So that's great. Optimistic. So the way I think about it is that there's a bit of magic here, right? We separate computational integrity from performance. So as long as we can support fraud proofs, and as I mentioned before, it's these hybrid fraud proofs that have sort of ZK in the middle, if you will, and we're using ZK for the time being only for the purposes of fraud proof production, responding to challenges, that sort of thing. Although, of course, over time, if it is indeed the case that ZK is both fast and affordable, we could switch into this, eager mode, right? We can become a validity rollup as well. And so our implementation of fraud proofs is based on this thing called Kailua from RISC-0. Yeah, and so for the moment, I mean, we've called this, I think, that before, the fat sequencer approach. This is what we're sticking with as well. So if you're interested in some of the details, there are several blog posts. You can scan the QR code, and that will take you there. But this talks about Celestia and some of the kind of underpinnings that give us fraud proofs, essentially, at the end of the day. The approach we've chosen to fraud proofs as well, and why sort of a fast DA is actually as important as we think it is. Yeah, and so this is a little bit more about Celestia. So this is from one of the recent blog posts. They are planning to get to 1 gigabyte blocks relatively soon, and so that's great news because I think we'll be able to consume that capacity. But so that's what's here on the left. On the right, we have a picture of what's called namespaces and Celestia speak, but essentially we are the biggest consumer of blob space on Celestia at the moment, although they have new or other rollup projects coming on as well. So we'll see how this plays out over time also. But yeah, very happy to see this growing DA capacity becoming available. Happy to have other DA efforts out there. I think this space will keep developing for the foreseeable future. So for the rest of this presentation, I'm here to tell you about what we call the Eclipse performance thesis. We pushed this out a couple of months ago. I'll give you URL towards the end of the talk. So some properties, some ideas I wanted to highlight at this stage. So we are heavily into this idea of hardware-software co-design. As I mentioned before, in the space of machine learning/AI, this is something that's really paid off. And I think the crypto space has been sort of sitting on the sidelines with maybe a couple of exceptions, like for example in ZK we do see, and maybe FH even, we see some specialized hardware actually taking hold, so that's exciting to see, but I think this needs to be there for the execution surface as well, and that's one of the ways we get to better performance characteristics. Cross-layer optimizations, I'll explain what that means in just a few minutes, but so for example, one idea to take away from this is that people talk about sequencing a lot. Of course, this is much of it is in the MEV context. You know, we basically push this idea of performance-driven sequencing, the ability for the sequencer to reorder transactions so as to optimize performance. That might be for the purposes of increasing the level of parallelism. This might be so that the backend database, right, that holds account information, has a chance to warm up the cache, right, so nothing is stalling in terms of actual execution. The idea of non-interference, so here the point is that, generally speaking, you should not have a particular pressing need for L3s, and part of that is that you can have multiple computational hotspots that operate without sort of negatively affecting each other, right, with non-interference essentially. And that's supported by local fee markets that Solana has advocated for, and there are some other properties we can provide that align with that as well. And then the idea of dynamic scaling. So basically, as applications demand more, can we provide more performance, right? So this is the kind of thing that you see in the cloud space, but you don't really see quite as much in the blockchain domain. Yes, I think we should. So I think it's helpful to actually separate the different layers, and I'll spend a couple of minutes talking about each individual one here as well. But so essentially, we have some design principles that apply to the part that's close to the network, to the runtime, the part that's in the middle, as well as the database, as well as the backend, right? And so, again, as I mentioned a couple of times already, so for instance, on the runtime level, things are already reasonably fast, right? I mean, the SVM already comes, for example, with a JIT, right? And the JIT is there for the Berkeley packet filter format, and that's all good and well. So in principle, things are already at a pretty high level, although we feel like we can go beyond where it is with the JIT. So for example, if we switch closer to where the WASM runtimes are, we think we can find better performance characteristics there. But again, the point is that it's already reasonably fast to start with. Okay, so let me take these things like one at a time, and let me talk about these principles in a bit more detail. So the first, for the front end of the system, so to speak, of the node, right, of the client, is this idea of near line speed processing, right? So you have tens of gigabits that modern NICs can provide, and the question is, what can we do in terms of line speed processing, right? What we can deliver that for. So Austin talked about, for example, doing SIG-verify as well as dedupe on FPGAs. We are partial to those ideas as well, although we feel like there are other ways to optimize that. So GPUs, as long as you can parallelize those things, could be quite attractive as well. Discarding failing transactions early on, providing so that's also quite nice. Pre-confs, right? So of course, lots of discussions about pre-confirmations in the Ethereum space. So it's all good and well. The question is, again, the devil is in the details here. So inclusion pre-confirmations are actually easy to provide, easy to generate. Question is like, what are they good for, right? Because oftentimes, especially for trading workloads, you probably want to have execution pre-confirmations. But not only that, you actually want to have sort of probabilistic execution pre-confirmations. You want to have high probability guarantees there as well, because, I mean, otherwise, if it's like 50-50, like, is that really particularly useful? So we have ideas on how to basically generate credible execution pre-confirmations. I've talked about performance-based sequencing a bit already, but we've seen first come, first serve, of course, fair sequencing ideas, lots of stuff that's been happening in that space for the past 3 years or so. But we feel like, some of the sequencing decisions should also be driven by performance considerations and should be up to us, if you will, up to the client to decide at least some of the time, right? So I mentioned the idea of enhancing the level of parallelism, and so if you can do that by reordering transactions, well, maybe so be it. Yeah, so application-specific sequencing is another idea that we are quite partial to. So for certainly some types of applications, maybe not all, applications should control their MBB extractions, and that's what this idea of application-specific sequencing, ASS, is largely about. And then last, but, well, the last one to mention here is like this latency-optimized transaction routing, again, basically aligns with what we've heard from 00 this morning, optimizing last hop latency, multi-propose ideas, things of that sort, how to position the nodes. Let's leave that for a later discussion. The runtime, one idea here, 5? Yep, okay, should be good. One idea here that I think is really powerful is that we can build a self-improving runtime. That is to say, given the amount of training data and given how repetitive some of these workloads in the blockchain space are, right? And given that we can, again, as I said, for pretty much every application just about, except when they just get deployed, right? We can go back and look at like months worth of execution. We can optimize almost every aspect of runtime processing. Memory allocation, deallocation, caches. We can also, pre-compute things in all of the cases, cache them aggressively, and this is what the second idea is about. What we call computational abstraction, right? This is a more aggressive form of caching on effectively the transfer function, right? Not the values, but the actual computation that we can, for example, learn from examples. And this is one of the strategies we can take to provide these fast and credible execution pre-confirmations. And so we can take these computations, effectively compress them, and run them on the NIC or very close to the NIC before even getting to the actual runtime, things of that sort. Hybrid concurrency, so the Solana approach uses pessimistic concurrency, so side effects, reads and writes have to be declared. The problem is that the actual concurrency that's observed is not necessarily maximized. Again, if our goal is to utilize a huge number of cores to their fullest extent, like how do we get there, right? And so one idea here is that we can combine sort of the best features, if you will, of pessimistic concurrency. Take these declarations as hints, if you will, but also bring optimistic concurrency control, which is out there in a bunch of chains, right? So, for example, Monad is one of those. And then hotspot aware fine schedule. I don't think I have the time to discuss that, but the idea here is to make it so that heavy sort of pieces of computation, right, things that are being actively used, applications that are being hit aggressively, like pump.fun or something like that. Hotspots, right, are basically given their own capacity on demand, that sort of thing. And the last one is the database here. Let me see, let me just click through that. So a couple of ideas to highlight here is that, first of all, lots of work out there on how to design databases that are aligned with modern NVMe SSD-based storage. Lots of ideas we have about how to enable parallel access to arrays of hard drives, right, in a way that aligns with hotspots as well. So again, in principle, you basically have this horizontal scaling on the database side of things as well. And the last bit here to mention is that we also have ideas on how to compute fast state commitments to enable light clients, something that Solana doesn't give us out of the box. So some things that we mentioned here at the bottom as well. Now, let me just give you this perspective. So pretty much, well, many things I've covered, maybe not everything, but many things I've covered have a lot of work that is from the AI domain, but not only, just systems in a more general sense, right? This is databases, this is, again, data representation ideas, this is on how to do state commitments in a performant way, this is more, I think, on the same, but, you know, I guess erasing old state, that sort of thing. This is how to do near network data processing. This is how to do more of the same, I guess, in more distributed context. This is more on the runtime front, right? So comparing eBPF in terms of its performance characteristics, and the JIT compared to like WebAssembly, things of that sort, right? But the point here is that there it is, right? A lot of this work is out there, and it feels to me that people in the AI domain have taken advantage of a lot of this stuff, and they have been doing that for the past decade at least. And in the blockchain space, we really haven't, and it's time to change that. So I don't think I have the time to talk about it, but we look at applications that go well beyond the current space of DeFi. So Eclipse has a vibrant DeFi related ecosystem, but lots of other things, AI, gaming, deep in, that we can do that go beyond that and require extra computational capacity. This is the QR code I promised, and please find me after the talk.